All right, here we go. So, how is everyone?
Doing all right, Nick. How are you doing?
Doing all right too, thanks. Got my second shot and I'm still good, so that's all good. Oh, physics midterm today. Brutal. Is this physics 3 for most people? Yeah, good stuff. Yeah, good luck with your exam. Um, so just for kicks, let's take a quick look at this. Um, so this gets run with an argument which is hour, minute, and length. And creates a J-frame and paints a rectangle um, that gets filled in. And it's run from something called a thread. We haven't talked about threads yet, but it creates a thread that basically sleeps for 1 second and then calls the repaint method of that frame. Um, and that's this little thing over here, right? This countdown timer. That's just a J-frame, and it's got a panel, and it's just kind of running in the background. And I have some bash hooks connected to it, so it automatically knows, since it's 9:50, this is my class that starts at 10 and ends at 10:50, so it sets the timer and so on. But it's just a Java thing, right? And it's not that much code. Most of the stuff I'll let Window Builder make for me. The hardest part is just playing with time, right? Figuring out if it's 10:05 and the class is 50 minutes long, and it started at 10, then how far should I fill in this bar? And it's just a calculation, um, time left over divisor, and it just draws a rectangle there. Yeah, just click, 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 like the internet. So you can actually use this stuff, in maybe not daily life, but almost daily life. Um, and has anybody taken a look at assess? So remember the assess command from 224 and 222? So that's if you say which assess, it'll tell you what program is being run when you say assess. It's a user local bin assess. Um, and if you look at that, it's a bash script. And the main thing this bash script does is run a Java file. So it runs Java on this jar file and from this class assess. May the ODPs be ever in your favor. Absolutely. And if you poke around this directory, you can find the source code for assess, and it's on Git. It's all open source, but it's a bunch of Java code, right? So there's the main assess main program. And it takes various arguments, and it's tied in with some bash scripts, and it's all pretty kind of icky, low-level code that communicates with bash and some other stuff. But there's print writers and there's buffered readers, which are like scanners, but slightly different. We're going to talk about sockets in a few weeks, and so this will make sense. And we're reading input, and we're doing string processing, and we're printing things out, and so on and so forth. And this is just Java. It's stuff that you could write, you could certainly read and understand with a bit of effort. And the whole system is just built around a bunch of Java classes. The grader program that downloads the text file from running assessments and turns it into a file that can be uploaded to Canvas, right? That's another Java thing. Yeah, I thought I might do ODPs for this class, and I ended up not doing them. I do have a few of them written, but you don't need ODPs at this point, right? ODPs are really kind of a way to help students, keep up with the material and self-assess as they go. And I think everybody has gotten really good at that. So those are like the training wheels. All right, so speaking of, how is PA4? The training wheels are off. They've been off. You got the dots coded. Awesomeness. Isn't it fun when you actually start getting something displayed? Like you run a piece of code and you see graphical elements. And then you can show it to friends. You don't have to explain the theory of binary search trees for them to appreciate what you're doing. Yeah, totally. All right, let's talk in some generality about graphics. And we've been using the paint method to display things and such, but let's back up a little bit. And let's just think about a display in general. And we've already said, one kind of odd thing about this is your origin is in the upper left corner instead of the lower left, where it would normally be, in a math class. And we still have X and Y. And X goes horizontally, Y is vertical, but Y starts at the top and moves down to the bottom. And I'm gonna post this this little document that I've written, but it's got the things that we're going to talk about here. So some things that are useful to keep straight in your mind. One is that X goes across and Y goes down. The next thing is row and column. And if you're confused sometimes about which is row and which is column, right, you will have no confusion after this class. Columns go across, rows go down. I think the way I think of this is, when I think of a column, I think of, Greek architecture, a column that runs up and down. So here's a column, here's a column, here's a column. So column 0, 1, 2, 3, 4. So columns go across and then rows go down. And once that's, rigidly fixed in your mind, a lot of things get easier, including Excel and making tables in Word and all of that stuff. And the third thing is dimensions, coordinates on multidimensional objects. So if we have a two-dimensional array of cells, this would be cell 1, 3. The first number is the row, the second number is the column. This is cell 3, 2. The first number is the row, the second number is the column. Right? And if you can keep those straight, then life gets a little easier. So yeah, it matches linear algebra, which is good. And this is not always the same over different languages, and it's not always the same historically. But in Java, in C, this is pretty standard, and I think most modern languages. Cool. All right, so we got X and Y, we've got columns and rows, and when we have, a two-dimensional matrix, the first number is how far down you go, that's the row, the second number is how far across. And so I sort of think of it as, move down and then across. All right, the other terms we want to be sure about is width and height. So width is how far across, height is the total height. So width is somehow related to columns, and height is somehow related to rows. And this gets us into all kinds of arithmetic gymnastics that come up at different points in doing computer science-y things. For example, if all of these are stored consecutively in memory, right? They're usually stored in this order. This would be the first thing stored. This would be the second, the third, the fourth, the fifth. And this box down here would be the sixth thing stored. So there's two ways to store a two-dimensional element in a one-dimensional memory. One is like that. The other is to store the first column. So this would be the first, second, third, fourth, fifth, sixth, seventh. This would be the eighth thing stored. And you would traverse your two-dimensional area like that. Most languages we deal with do it that first way. We go across the first row and then down to the second and then down to the third. That's not going to affect us in Java. It will definitely affect you in assembly language. It will affect you performance-wise in most languages if you deal with really big arrays. But that's one issue. So suppose these things are stored, in this order. We could write a formula for how far from the beginning of all of this storage we could find a particular cell. So for example, and I'm just doing this because we're here right now. So for example, cell 1, 3 is at what offset from the beginning of storage? Well, if we think of this as offset 0, 1, 2, 3, 4, 5, 6, 7, 8. So this is at index 8. If we come down here to cell 3, 2, and we calculate its index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So in general, if we have a cell in some given row in some column R and C, could we hypothesize a formula for finding the index of that? In other words, how far it is from the beginning of where all these cells are stored? That was fast. So someone said width times row plus column. And we can spot check first. So here the width is equal to 5. So 1 comma 3, and remember this is row and this is column. So 5 times 1 is 5 plus 3 is 8. 5 times 3 is 15 plus 2 is 17. So that certainly matches these cases, and in fact that is the perfectly correct general formula. So yeah, nicely done. So yeah, 5 times row plus column. Yep, that is the same. Right? And so why does this work? Because, you know, each time that you move down one row, you have to add, in this case, another 5 to your index. So this 5 times row is really giving you the index of the first thing in row R, and then you add an extra C to move over to column C. And this only works because we're starting with origin 0. If we start row and column from 1, this doesn't work. So this is one sense in which, you know, starting from an origin of 0 really makes sense. And if we had a multi-dimensional beyond 2, if we had a 3-dimensional array, right, it would be exactly the same thing. And something to notice in here, what happened to our height? Why isn't that in this formula here? Because it doesn't matter. The height has no bearing on this calculation. Now the height has a bearing on what's the largest index that's going to be valid. But if you go back to C, remember, we don't care about, you know, whether an index is valid. That's kind of up to the programmer to not go out of bounds and get a seg fault. So if you look at the C code that's generated when you try to access an element in a two-dimensional array, it'll use the width of that array, but it won't use the height. Which is why sometimes when you pass an array to a function, you have to tell it how wide the array is, but you don't have to tell it the height. All right, so that's an example of the kind of calculations we're going to do. And when we're graphing, when we're drawing an image by lighting up pixels, we're really doing the same kind of thing. So if we looked at the video memory, where you know the information that you're displaying on a display is stored, that's also a one-dimensional chunk of memory. But to draw this pixel at some location x, y, we need to know where in our video memory this pixel is stored. And it's going to be y times the number of pixels across plus x, or something close to that. So drawing-wise, right, we have some sort of, you know, it's one-dimensional, but we think of it as a two-dimensional array of memory. And for each point x, y, we store some piece of information there saying, should that pixel be displayed or not? And if it's a color display, we actually store the color of that pixel. And we talked about colors last week, typically a 24-bit value, so 8 bits for red, green, and blue intensities. And so somewhere in memory there's a 24-bit number associated with this XY pair. And your whole video display is just a big long chunk of memory filled with these red, green, blue values. And usually these are 32 bits. We have other information in there called alpha. But it's just this big consecutive list of pixel values. And when you build the hardware to display what's going to be seen on your screen, right, typically you're sweeping through this array and pulling off the pixel values and using those to light up the physical elements on your display. All right, so let's imagine that we're drawing, you know, a playing field for dots, for example, and let's keep this really general. Suppose we want each box to have a certain height, which we'll call cell height, and a certain width, which we'll call cell width. So there's a relationship between the total width of the playing area, the width of each cell, and the number of columns that you have. In particular, the width of each cell times the number of columns is going to be equal to the width of the whole board. And the height of the whole board is going to be the height of each cell times the number of cells in a column. That's the number of rows in your board area. And so we can cobble together some formulas. If we know the dimensions of the playing area, and we know how many rows and columns we want, we could find the cell height is the total height of the board divided by the number of rows. So it's just this cut into this many pieces. And the width of a cell is just this total width cut into that many pieces. And we don't need to calculate these directly, right? We know we're going to have an 8 by 8 array of boxes, and each box is going to be 50 by 50. And we could, put this on graph paper and figure out that the whole board's going to be 400 by 400 or 320 by 320 or whatever, based on those numbers. But what we do care about is when you click, figuring out what box you clicked in. And so it's useful to be able to find the coordinates of each of these boxes based on the index of this box, the row and the column that it's in. And so here's some formulas that may or may not help you. If this is cell row comma column, its x coordinate for the upper left corner is going to be the column number times the width of each cell. And the reason for that is, if this is 0, 0, well, the y coordinates are always going to be the same going along the top here. But the x coordinate is going to increase by the cell width. This is going to be 0, this is going to be cell width, this is going to be 2 times cell width, 3 times cell width, 4 times cell width. So if you're moving over to column COL, the upper left corner has an x-coordinate of column times cell width. And exactly the same logic, the y-coordinate is going to be the row that you're in times the cell height. So we start with y equals 0, this will be cell height, 2 times cell height, 3 times cell height, right here. So this will give you the coordinates for the upper left corner of a box, and then we can calculate everything else from there using relative math. So if this is point xy, the x value here will be x plus the cell width, and the y coordinate will be the same. The coordinates of the lower left corner, x will be the same, but y will increase by cell height, and the lower right corner, x and y will both increase by cell width and cell height. So if you have a particular cell 3, 2, and I know that each of these blocks is 50 by 50, I can tell you the coordinates of this upper left corner. X is going to be 100 and y is going to be 150. Is that making sense? Like I say, I'll stick this on canvas, but you may find it useful. So your main task when you're responding to mouse events is, you've got this field of imaginary boxes, and somebody clicks, and all you get is an XY coordinate pair. And you'd like to know what box did the person click in. And so we can reverse this calculation and say, if you clicked at some point XY, what row and column describe that box? And so you can work through this on your own if you like, but the punchline is take y and divide it by the cell height, that's the row. Take x and divide it by the cell width, that's the column. And so truncate, right, cast these things as integers, or if they're integers to begin with, just do the division, right, everything is non-negative. So if you click at the point, 180, 32, that's going to correspond to column 3, row 0, which would be, somewhere in here, 180, 32. So in your panel class, where you're drawing your dots, right, which will become your boxes, you drop in a mouse listener for clicks, and you get an XY coordinate from the listener. We'll code this up in a second. You get an XY coordinate from the mouse listener, and you can translate that into a row and column of a cell and know, oh, the person clicked inside cell 3, 2. And now if you go in your array of boxes, something I've been calling the board or my board, and just pull out element 3 comma 2, that is a box, but it's the box that they just clicked in. And then your remaining task is figure out which edge they clicked next to. So let's say we've got a box, and let's say this is 200, 300, and this is 250, 300, and this is 200, 350, and this is 250, 350. And if they clicked, somewhere over here at some point x, y, how do you figure out which line they're asking to be drawn? Well, let's suppose that they're not deliberately being ambiguous and clicking like right here, or right in the middle or something like that. There's presumably one line that they're clicking closest to. So I've got hardwired numbers here. I'll stick with those for the example, but obviously those are going to be variables. But let's calculate your distance from each of the 4 lines. So this distance is going to be x minus 200. This distance is going to be 300 minus x. This distance is going to be y minus 300, and this distance is going to be 350 minus y. So don't memorize these, right? Play around with these on paper and convince yourself. Make a small grid, use reasonable numbers, and calculate these. And I might have some of these backwards. But the punchline is you can calculate, how close you are to each of these lines. And then just find the smallest of those. And if this is the smallest number, then you can say, okay, they clicked right next to the left line. And so now you check the box object, see if left is already true. If it is, they're clicking next to a line that's already been drawn. Tell them they can't do that. But if the left part of that box is false, right, that's the line that they've selected. So set it to true, and then go back one column, right, and set the right field of that box to also be true, because this line is the left of this box, it's also the right of that box. It's a little easier than Pythagorean, yeah. So if they click, exactly in the middle of 2 lines, right, like that, I guess it would have to be like exactly in the middle, because if they clicked up here, they'd be closer to that edge. But if they click exactly in the middle, or somewhere along a diagonal, it just depends how your if statements are written. 2 enter, 1 leave, exactly. I'll get out my Tina Turner outfit. It's up to you. So one thing you can do is just let it fall to the logic of your if statements. If I'm checking this distance first and I'm saying less than or equal to, then it might end up picking this line or that line. If you want to get a little fancier, one thing you can do is require that you clicked closer than 5 to any other line, and then if you clicked somewhere where you were within the same distance to more than one line, if it was within 5 for example, you could just not take it as a click, and you could like flash the screen and or just do nothing. Yeah, totally. All right. So it's up to you. But that's the basic mechanics of how you can take a mouse click and turn it into a decision about what line is being selected. So some of this is described in the assignment, and some of the formulas are on here that I'll put up on Canvas. But most of it you probably should sit down with graph paper, or something, and work through this right? Repeat these calculations so that they make sense to you. It's no fun to sort of just like work with random formulas and hope that they work. You really want to kind of go through the derivation of these yourselves, and make peace with them. But once you've got those formulas down, it's pretty straightforward, right? Take a click, turn it into a box, and then figure out the coordinates for the corners of the box, right? Which was what I was doing here. And then you can just find your straight line distance to the four edges and go from there. And do the obvious things, you know, if they click outside of your playing area, you're probably not even going to see a mouse event. But, you know, if you've got some border inside your panel around your boxes, don't let them click outside, and so on and so forth. So let's wire up a mouse. That's a good question. And we've done a little bit with mouse listeners, but not like a big example. So let's throw some code together. Or are you a mouse whisperer? All right, so we'll start off with a J-frame. And I'm going to go ahead and put a panel in here and draw on that. We can draw on the main panel, but let's stick to what we're going to be seeing anyway. So I'll put an absolute layout in there, and I will put a panel. And I'll make it big, and I'll add a border. This is my quarter for adding borders to J panels. I don't know why. Let's do a different kind of border. Let's try an etched border. That doesn't look as fancy to me, but okay. And I'm going to come back in here, and I'm going to place this thing somewhere reasonable. All right, so there's our panel. $5 to listen to a poem. Yeah, totally. So let's make a new panel. I'll call it draw panel. And we'll say extends J panel. And we'll start a paint method. And go ahead and import these. And then the last thing I'm going to do is in here, I'm going to change my my J panel that I created to be a draw panel. So we'll make that a new draw panel, and here we'll say make a draw panel. That's almost recursive poetry there. I like it. I was hoping I was going to finish a book I'm writing before this class ended, but I don't think I'm going to. but I'll like post it on Discord or something like that. But it's a book I was writing for this class. All right, so let's do some XY drawing in response to the mouse. Let's make a doodle program. So we'll go back into our panel and we'll add a mouse listener. So we'll add an event handler for mouse, and let's do mouse motion. We'll just do mouse moved. And we'll do mouse dragged. So I'll hold the mouse down. So E is a mouse event, and it's got a bunch of methods, but it's got a method called getX and a method called getY. Which will give us XY coordinates. So if I run this and I bring my mouse, my panel disappeared, bring my mouse in here and start dragging, I'll get XY coordinates for where the mouse is. And I can go outside and it still like notices it. Because it's a drag event, so I'm holding the mouse button down. Alright, so first of all, what happened to the border on my panel? Do you remember this? It's not exactly repaint, but it's close. We're not actually doing anything in our paint method yet. Oh no, we're back to cats in chat. Yeah, we need to call the super method, right? So, that will call the original JPanels paint method, which among other things will draw that border that we specified. So there's our border, and if we click outside, nothing happens, or if we click in here and hold, we get mouse coordinates. All right. So this is a separate class that we're creating for the JPanel. The mouse listener itself is basically happening inside our JFrame class, right? So this thing that we called main, which is a JFrame, is where we put the mouse listener. And again, if you let Window Builder and Eclipse set that up for you, right, it just creates the code and creates this thing that we called an anonymous inner class. So it's actually creating a mouse adapter class, but it's putting it right in here. That's a good one too. All right, so let's do some doodling. So how are we going to draw? Let's go into our panel, and let's just fill an oval. And we'll just make a little 1x1 oval. And so where is it going to get X and Y from? So here's what we want to do, right? In here, in the mouse listener, when you get an event saying that you're at position XY, we'd like to put a dot at position XY on the panel. And so, you know, we can't call draw oval from here. We can call repaint, which will cause swing to call paint, but we have to set something up first so that when paint is called, it draws an oval at XY. Alright, so this is something you're going to see again and again and again. We're going to set things up so that paint will do what we want it to do, and then we're going to call repaint. Alright, so set things up so paint does what we want. So I'm going to make a method in my draw panel class, which is just called panel.saveXY. Alright, so I'm going to make a method called saveXY. I'm going to pass the XY coordinates of the mouse to that method. And that method in the panel class is going to store those variables somewhere. And then the paint method is going to use those to make an oval. So let me make a pair of integers. Let me call these last x and last y. Right, so when I call saveXY with a pair of integers, it'll just save those in last x, last y. And now my paint method, I'll use that last x, last y pair to draw an oval. Oh, you've gone from Cats to Bell Labs. Oh, through the segue of costs. Okay, that makes sense. Alright, so let's run this. So if I hold down the mouse and drag, right, we should be getting a little oval here, but nothing is happening. So now what am I missing? And someone said it earlier. There's where we're going to repaint, right? So we've set things up so that paint will do what we want. Now ask for paint to be run. Typos and comments don't matter, but they bother me. All right, so now we're gonna call repaint in the panel object. Oh no, Mario! Did I make my thing too small? That was disappointing. Let's make this a little bigger. There we go. So now I got a little dot following me around. And you can try to get away from it. And it's like a really cheap video game. Outrun the dot. Alright, now that's not very doodleicious, right? It's not actually like an Etch-a-Sketch thing going on. But let me show you a really cheap way to make this a little more interesting. Get rid of that call to super. And if I run this, now I've got something like what I was thinking. This is not really a good thing, okay? And this won't always work like this. It depends on your exact system. I'm actually using a bug to my advantage here. The bug is I'm not calling the superclass's paint method. Part of what the superclass's paint method does is it clears the screen before it starts painting. Since we're not doing that, since all I'm saying is filling an oval, right? This is showing a persistent display. But, you know, as soon as I resize this, that's going to call something which is going to clear out the display, right? But you can get an idea of what's going on, and you can measure, you know, the speed of the drawing relative to how quickly you move. So painting with bugs. All right, so we don't want to do this, right? We pretty much always want to call the superclass paint method. So what if we wanted that persistent behavior? What if we wanted to actually see all the points that were being drawn without them erasing? How could we make this persistent? Excellent. Yes, you could make an array and you could save the previous XY positions in the array. And then in our paint method, we would go through that whole array, we would pull out each XY pair and we'd draw a dot there. And that's what you would have to do. You'd have to basically save all of the pixels that you want displayed somewhere in memory. And we could do that with a linked list, right? Since we have linked list objects available, we could store the XY pairs in there. So remember there's a class called point, which basically holds a pair of integers, XY. So we could make a linked list of angle bracket point. And each time that we get a mouse event, we could add, e.getx, e.getY, turn that into a point, add it to the end of the linked list. And then our paint method, we could iterate through everything in the linked list and pass the XY we get to fill oval. And if we don't want to run out of memory, we could check the length of that list, and if it is bigger than some maximum that we decide, say 300 points, then we could delete that first point, right? So we could turn this into a queue basically, and it would always contain the last 300 points that you generated mouse events on, and it would display that. And then you'd get, a line following your mouse around, showing where you've been. That is a lot of work, but it would run, basically with no visible delay. Because, 2021 and Java and fast machines. If you go inside, a video game and you think about all the calculations that are being done, it's a phenomenal amount of work that's going into these displays that look rock solid, at 60 frames per second. Incredible computational power being used. So yeah, something like this, not an issue. Yeah, and yeah, it did. And for me, it took some mental adjustment to get to a point where I was sort of internally comfortable with doing these kinds of things, because it feels very kind of resource wasteful, right? It's like that's going to slow down my other stuff and things like that. And really, machines can handle so much, so we don't have time to wire that up, but that would be fun to do. Try to make a draw program, and and then once you've got that, you can come into your panel and add a clear button over here that would clear your display. Well, how would you clear the display? Just clear out your linked list and call repaint, right? And there's a method for clearing a linked list. It's called erase or something like that. Gets rid of all the elements, call repaint, bingo, your display is empty. And you could have a color button that changes the color, and in your drawing method, your paint method, you could just set the color based on some red, green, blue values that were specified, and triggered by hitting buttons over here. And you can sort of envision all of this stuff. So we always call repaint, right? Our code always calls repaint. You'll never see anything in your code that says call paint, right? But we define a method called paint, which does, the painting that we want. We do call super paint though, right? Which is the JPanels paint method. But all of our calls are going to be just to repaint. So anytime we've updated information that will cause paint to do something we want, we'll go ahead and we'll say repaint. And if you try to call paint, you'll get a compile error because you don't have a graphics object. So that reminds you. All right, so no class tomorrow. Remember, Thursday we'll do a regular class. So instead of a lab day, and Thursday we can talk about the final. This is assuming I actually get around to writing a final or a midterm. Yeah, midterm, not final. So we'll meet Thursday as regular, and then Friday will be the midterm. So that's our plan. All right, sun's out. Have a good afternoon. I will see you next time.